My name is Mike Dillon. I'm Vice President of Business Development with CR Wall. And on behalf of Ionix Gas Technologies, CR Wall, and Foothills Industrial Products, we would like to welcome you to our webinar today titled Static Electricity in PE Gas Pipe O&M Operations. And now it is my pleasure to introduce our presenter and subject matter expert, Dirk Smith. Dirk Smith is president of Ionix Gas Technologies. Ionix specializes solely in static mitigation systems for natural gas distributors. Mr. Smith graduated from the Wharton School of Finance and Commerce at the University of Pennsylvania and holds 3 U.S. patents on static elimination technology. He has written numerous articles about static electricity and gas pipelines, which have been published in Pipeline and Gas Journal. We have known and worked with Dirk for many years and can attest to his depth of knowledge and passion for the subject, and we're sure you will learn a lot. Dirk has asked us that we hold all questions until the end, and we will be using the chat feature to capture them. So on a real-time basis, please enter your questions at any time during the presentation, and we'll read and respond in order during the Q&A session. Thank you for attending today's session. If you have any questions or following the presentation today, please reach out to your CR Wall or Foothills representative. Also note, CR Wall will be hosting additional webinars this fall. Our lineup includes GPL odorizers, tough applications and odorization, gas detection best practices, and valve maintenance best practices. Please follow us on LinkedIn for up-to-date schedule and announcements. And now, live from sunny Boca Raton, that's hard duty, Dirk. Sunny Boca Raton, Florida, Dirk Smith. Dirk, the floor is yours, sir.
Mike, thank you very much. And you can, I assume everybody can hear me. Yeah, I'm down here in Boca Raton, about 3 miles from the beach, and the temperature is about 83 degrees Fahrenheit. Unfortunately, Americans, we can't convert to Celsius, so we don't have mathematical skills to do that. So you're going to have to do that. But I want to thank you all, and especially CR Wall, for sponsoring this webinar, because it's a topic that you never see at any kind of operations conferences. And so their interest in making people understand this, I think will, and sponsoring this webinar will be a great benefit to you. Now, whoops, let's see, there we go. So just let me give you a little background about us. IGT, we developed a suite of products to eliminate static electricity inside and outside PE pipe. We developed this technology actually for industrial uses, for the printing industry, plastic injection molding. And then we were approached by people in the gas industry saying, we're having a problem with static and polyethylene pipe. Could we help in that? And so we took this technology and modified it, put it out in the field, developed it, enhanced it. And in the course of customers calling us with their problems, we noticed certain patterns emerging. And so what we've done is we have structured this webinar, this class, based on what we were hearing from people. Now, what's going to happen here is you're going to get a working understanding of static electricity and polyethylene pipe. That's one of the goals today. Now, I'm sure everybody knows what static electricity is. And, you know, sometimes I'll be going along and you'll say, oh yeah, I knew that. Oh yeah, I knew that. Oh, I didn't know that. So what you're going to have is some aha moments, but you're going to have an organized curriculum that's going to take you through an understanding of static electricity and polyethylene pipe. Now, once you understand that, then you're going to be able to recognize where your static ignition risks are in your field operations. Now, when I talk about static ignition risks, there's actually other risks, but primarily I think most of you are here because you're concerned about a static ignition risk. But what's going to happen is you're going to understand where the static is in your field operations so that you can be sure to have a static suppression procedure appropriate for the operation. Once you understand that, then you can go back and develop and evaluate your own static suppression procedures based on how static operations in your system, based on the known risks. And it's important to understand here that the basics of static that I'm going to talk to you about apply from the wellhead, a gas wellhead, to a service meter. I got a call a couple of weeks ago from a gas producer in Calgary who was having a problem, a static problem in his polyethylene pipe. So the basics that you're going to hear today, although most of the examples and I will couch most of my discussions on local gas distribution, any static issue in a polyethylene pipe, what you're going to learn today about it will be appropriate for those situations. I found that we can't assume that we all understand the words and verbiage identically. So what I'm going to do is I just want to make sure we understand what static electricity is. Often when I talk to people, they kind of say, well, static electricity is kind of an inferior kind of electricity. You know, the real serious electricity is electricity that's coming out of the outlet of my office wall here and is powering this computer. And static electricity, well, that's kind of inferior electricity. That's not so. Electricity is electricity, energy is energy. What makes the difference between what static electricity is and what we call current electricity, that is the electricity that's coming out of my wall and coming to my computer, is that static electricity is electricity that has found itself sitting on a material that is not an electrical conductor and therefore it can't move. Let me explain. Now I'm in Boca Raton, Florida. And up the road in Juno Beach, Florida Power and Light has a generator. And this generator starts ginning a whole bunch of electrons up by turning a generator. Now, it takes those electrons and it dumps them on a piece of copper wire. Now, because copper wire is an electrical conductor, those electrons, when they're placed on it, they'll start to flow along that wire and be delivered into my outlet. And it's just the same thing when you take gas from transmission and you put it in your pipe and pressurize it, it follows it and delivers it to the customer. Let's take that same example of that generator in Juno Beach, but change it up a little bit. This generator is taking a whole bunch of electrons, and it takes those electrons and then puts it on a piece of polyethylene. Well, those electrons are going to sit there because copper wire is an electrical insulator, but polyethylene, copper is an electrical conductor, but polyethylene is electrical insulator. So it resists the move of electrons on it, in it and on it. So when those electrons, if FP&L just put those electrons on top of a piece of polyethylene, they just sit there. They can't move. They're static as opposed to moving, which is current. So it's important to understand that the material is the basis for the electricity being static. The material the electrons are sitting on resist their movement, so they just sit there, as opposed if you put those electrons on copper wire, the copper would conduct it and the electrons move freely across the surface and move along. So how's static electricity generated? It's generated a lot of ways, but in the gas distribution and production business, it's essentially caused by friction. When you have two electrical insulators rubbing against each other, what occurs is the mechanical shearing action of the two materials causes an electron to be mechanically sheared off. And these electrons, these displaced electrons, accumulate randomly in surfaces, but for reasons not known to us, they have a tendency to accumulate in certain areas. And so it is the mechanical friction, methane being an electrical insulator and polyethylene being an electrical insulator. When those two rub against you, the compression and the force of that gas going past each other, they shear off electrons, and these electrons accumulate in random places inside your system. Well, so what? Okay, that's great to know, Dirk, but so what? Well, here's the problem. Mother Nature is designed to be an electrical imbalance. It doesn't like electrical imbalances. It's designed to be at electrical neutrality. Now you see that photo of lightning in the right of my slide. And here you have a case, I'm sure it's very similar in Canada, where the hot air goes up in the summer, then it cools off and comes down, and you got this shearing action going on between up and down drafts in the clouds. And finally, the shearing action causes electrons to be displaced. They accumulate up there, and finally the static charge gets so high it arcs to ground, because Mother Nature wants to go to electrical neutrality. And so what happens is Mother Nature, if your system has static in it, it's going to neutralize itself. The key for you is you want to control when it does that so that it doesn't cause an ignition, a shock a worker, create a leak, burn out some electronics. So that's why you have to address it. Now, what I'm going to do is, now that we know what static electricity is, now we're going to apply it more closely to your particular situations, and that's the basics of static electricity in polyethylene pipe. Now, down here in the States, a lot of the distribution companies paid for Gas Research Institute, who was the precursor to the Gas Technology Institute. They paid them a lot of money to do research on static electricity and polyethylene pipe. So what I'm going to do is I'm going to condense all these reports. You know, I think research institutes get paid by the page. So I'm kind of distilling you and giving you the summary of a lot of research done on static electricity and polyethylene pipe. And this is the most important slide you're going to see today. If you don't remember anything else about what I say today, don't forget this. This is the root cause of any static ignition you have. Now, at the very end of this, I'm going to talk to you about an incident where people were absolutely flummoxed at what happened because they didn't understand this. All static starts in the inside of the pipe, and that's because that's where the movement is. That's where the friction is. That's initially where the static charge develops. It's the passage of the electrical insulator methane inside a polyethylene insulator pipe, displaces electrons, and that friction displaces the electrons. They start to accumulate on the inside of the pipe. Here's your citation from Gas Research Institute, where the pipe is charged by the gas, a particulate, and the gas flowing through the system, and the charge is generated initially on the inside of the pipe, initially. Now, remember that example I told you about FP&L and their generator, taking those electrons and putting on a piece of polyethylene. Once static's generated, it just won't go away. It's sitting on a material. It can't conduct away. It wants to go to ground. It wants to neutralize itself, but it can't because it's on material that will conduct it. It's forced to sit there. So you have to deliberately dissipate it. Once again, here's your citation from the Gas Research Institute saying it's just going to sit there because it can't move. The third thing, basic, is not intuitively obvious. I can explain the physics, but it really isn't necessary. All you need to know is that it's true, and that's this. When the static is created on the inside of the pipe due to the friction of the gas and a charge develops, it induces a charge on the outside of the pipe. That's why in the past you've done external static dissipation procedures. Again, I could explain the physics, but it's really not necessary. Here's the citation from the Gas Research Institute confirming that in their research, that the electrical field resulting from the interior charge induces an exterior charge on the pipe. Very important to remember. So when you create a static charge with the gas passing through a pipe, you have a charge on two sides, inside and outside. And then finally, Mother Nature wants to go to electrical neutrality. That static charge is going to arc. It is going to want to go to electrical neutrality. So the key for you is you want to control this. You don't want Mother Nature to do it on her schedule. You want to do it on yours. And once again, here's the citation from Gas Research Institute saying that whenever you ground a charge, it's going to arc. Now, from these four basics, it creates four threats for you. And we're going to go through all of them, but we're not going to spend equal time on all of them. The first one, which is the most in-your-face, obvious threat, is the ignition threat, because that is a personal and property threat. Okay, that's where you have injuries, that's where you have property damage. The second thing that it causes is shocks, a lot of electrical shocks to workers. We'll talk about that a little bit. Now, the third thing it does is it creates pinhole leaks in polyethylene pipe. So therefore, static is an integrity threat. And then finally, what you're going to start seeing more and more of as you put more sensitive electronics on pipelines, that you're going to find that static is going to burn out some of these electronics. But the key thing is, if you manage the static electricity in your system, all these problems go away. But those are the four threats. Now, we're going to talk primarily, most of this presentation is going to be the ignition issue. Like I said, we're going to talk about shocks and very briefly electrostatic pinholes and very briefly electronics. But the first threat is ignitions of leaking gas. Now, if you think about what I just told you, you have a really unique problem when you distribute gas in polyethylene pipe. It creates its own ignition source. Just by the fact of you forcing that gas through that polyethylene pipe, you're creating static electricity, which is the ignition source for natural gas. Now, what gas research has said, remember, every ignition has to have an ignition source. And I've talked to people and they'll kind of say, well, what was the ignition source? Well, I don't know, rock falling down in the excavation or, you know, I don't know. And they kind of get ethereal in their answer. I'm saying, whoa, whoa, look me in the eyes. Every ignition has to have an ignition source. So given what we know about the passage of gas in polyethylene pipe, if you've got leaking gas and you've got an ignition and you have no known source, there's no obviously known ignition source, then it must be static electricity. It has to be. Every ignition has to have an ignition source. And so the most probable cause whenever you have an ignition without a known ignition source, you know, a sparking motor, a car running through a plume or something, is static electricity. So what makes a potential static ignition risk is that you have interior pipe surface exposed, which probably has a static charge on it, gaseous mixture, and then proximity to electrical ground. That proximity may be a tool, it may be a worker, it just may be the presence of earth and ground. Now, I'm going to show you this video. This is a very important video, and it's a very poor quality video. And the reason why it was shot, it was videotaped by a friend of mine over television when it was broadcast over the air. So when he recorded this, this was done well before any HD or anything like this. But the reason this is important, this is the only instance I've ever seen where you have a static ignition captured on film. Let me give you the backstory. It was in Oklahoma City. Very typical, third-party damage. Somebody dug into a medium pressure line. Oklahoma Natural Gas sends a crew out into this housing development that's being built to repair the leak. Now, the ONG guys are in the excavation. They are working to put a clamp on the broken pipe. Before they can put the clamp on, the gas ignites. Now, the question is not what caused the damage. Obviously, it's third-party damage. The question is, what's the ignition source? Because you're not going to have these guys smoking cigarettes. They're not going to have sparking motors. They're not going to have, what's the ignition source? The only thing it can be is static electricity. And so what it does is it shows you how GRI is right, that static electricity generated inside the pipe due to the flow of gas is the cause for a static ignition.
A natural gas explosion rocked an Oklahoma City neighborhood just before noon today. Workers were trying to repair a ruptured line at Northwest 131st and MacArthur when the gas ignited. Line 9's Heidi Browning joins us live from that neighborhood. Heidi?
Well, Kelly, there's a bit of a mess out here in the neighborhood. You can see behind me what's left of a fence, charred remnants of the posts, and quite a lot of digging that's been done to make repairs to those lines. But people coming home this evening will find a much calmer scene than what many people saw this morning. It started as a fairly routine repair job. ONG workers were trying to get the gas turned off after a 2-inch medium pressure line was accidentally cut. Suddenly, the gas exploded, sending huge flames into the air. 2 workers received minor burns. ONG officials say there's preliminary speculation that static electricity in the plastic pipe somehow caused the explosion. It took about 30 minutes to control the fire and get the gas turned off.
Now, again, what was the ignition source? Static electricity inside the pipe. Now, what we're going to do is I'm going to take you through 5 operations that, based on our experience, and I think you're going to find your experience, pose the most dangerous static ignition operation. I've kind of made a pecking order of them. You know, you may disagree, that's fine. The purpose I'm going through is we want to look at where the static ignition risk is inside these operations, okay? And remember that there's both static on the interior and exterior of the pipe in any kind of operation. Now, in the first one here, this is just basically an illustration of what happened with that ONG video you just saw. Somebody dug into the pipe. Now, you notice in my illustration here, and if you can see my cursor, let's get it over here. You see I have some black patches in that, red patches in that pipe. And essentially what they do is I can tell you with 100% certainty, you've got static in your system. But I can also say with 100% certainty, I don't know where it is in your system. And that's the bugaboo about static and polyethylene pipe and gas systems. You know, it's there, you just don't know where it is. but it'll generate, and it'll start to kind of randomly accumulate in certain spots. Now, in this illustration, which I'm showing you with my cursor right in the center where that is shown where it's dug in, at the time when there was the dig in, or it could be an O&M operation, they did not hit any static on the inside of the pipe. But if gas starts to flow out of that pipe, like in that instance where you saw the video with ONG, what happens is the static starts to build up. There's turbulence as that gas comes out of that cut. Let's assume it's a third-party damage. In the cut, which is ragged and torn up, static starts to build on the inside edges of that cut, on the edge and underneath it and the inside where the turbulence starts to come out. Now, in the case of ONG, what happened is they didn't hit a hot spot. So the gas started to come on out and it kept flowing and flowing, but the static was building up and up and up and up. And finally, the static charge at that break got so high that it arced to ground and ignited the gaseous mixture. Now, if you have an O&M operation, you're probably not cutting into anything that's blowing gas. However, the static charge is going to be, could very well be a static charge on the inside edge of that pipe when you begin your operation after you've done squeeze off and taken it out of service. So whenever you're going into it, cutting into a pipe or a pipe's been cut into, you have to be careful and understand that the charges, there may be an underlying charge inside that pipe, assuming you've dissipated the charge on the outside, and this charge is going to build up inside and under those broken or cut edges. Now, the second thing, and this follows pretty much from the same thing, is when you're doing purging. Now, my illustration here, I've got a grounded purge pipe. But the problem with a grounded purge pipe is you're assuming that, one, you got a good electrical connection to ground. You have no way of proving that. And two, what can happen is when you have metal pipe, even though metal is an electrical conductor, you may have patches on the inside of that pipe due to corrosion, coatings, dirt, grease, whatever, that act as electrical insulation patches, and a static charge can build up on those patches even though the pipe's grounded. So whenever you have a purging operation, you have to be aware that there's a lot of static on the inside edges where that pipe is exiting gas. And in the same way, assuming you use a metal grounded purge pipe, the connection between your plastic and your metal is never going to be perfect. There's always going to be some turbulence in the gas passing through it there. So once you separate your pipe, you need to be aware that there's static on the inside edges of that plastic pipe. Now, with all the interest in overpressure vents and relief valves and things like that due to overpressure incidents, any kind of valve or anything that you have that's going to engage during a relief or overpressure operation, the same thing's going to occur in that the static, if it's vented outside, the static on the inside of that pipe can build up and arc and create an ignition. Now, the third most dangerous is cutting into squeezed off plastic pipe. What happens is when you squeeze off a plastic pipe, the Venturi effect takes place and the gas starts to speed up to try to get through the narrow opening. And as it does there, it creates tremendous downstream interior voltage. It also creates substantial interior voltage upstream from the squeeze off, but primarily most of it is in the downstream. So when you have squeezed off a piece of pipe and you've now stopped gas flow, you have to exercise extreme caution when you're cutting into that because of the voltages, the substantial voltages that could be downstream and upstream of squeeze off. The fourth most dangerous thing is a hot tap. Here you have a fixture that's been fused on, and as the tap came down, it cut into a hot spot in that pipe. So whenever you have a tap, you've got to be concerned about the static on the inside of that. And you want to dissipate the static at the point where the tool is cutting into the pipe. And then finally, whenever you're cutting into a pipe, you might cut into a hot spot, and even though it's under pressure, residual gas, and the tool can ground it, or it can arc to ground, and then you can have an ignition. And that's happened whether it's been opened up or reached into or cut into. Now, I'm going to take a little sidestep here for a minute. Most people think, well, static is a polyethylene plastic pipe problem. Not so. It's also a metal pipe problem. Metal pipe by nature, since it's an electrical conductor, does not have the same potential to have as many static ignition issues, but that doesn't mean it can't have them. What happens is, you know, like bare pipe is going away, you know, you're replacing it all, it's all coated. Or you have metal pipe, and some old metal pipe, I've got guys in the Northeast US have some of this old cast iron stuff and everything. Oh my gosh, they don't want to know what's inside those pipes. But what happens is if you have coatings or residual chemicals or tars or grease or scale or something like that, those patches in a metal pipe are electrically isolated, and static can build up on that. And in turn, if you happen to expose that to ground, that can ignite a gaseous mixture. So you have to be aware that just because it's metal, that does not mean that static can't be present inside that pipe. This is a picture that AP Photo, I purchased from them, and it's a Tennessee gas pipeline in Hanoverton, Ohio that caught fire. The issue is not what caused the pipe failure. The real problem is what caused the ignition. If you take a look in the left of the photo, right where that flame is coming up, and you see that structure there, that's a farm silo. This was in the dead of winter, calm sky, clear skies, no weather, no wind, 29 degrees, no weather reported. What's the ignition source? Everything has to have an ignition source. There's nobody out there. It was in the middle of the night. What's the ignition source? The pipe failed, gas is escaping, and on a place on that pipe, probably where there's coating, the static charges start to build up and up and up as that gas is exiting at high velocity. The charge finally gets so high, it arcs to ground, and ignites a gaseous mixture. So be cautious. Just because it's metal pipe does not mean there's not static present. Now, we've talked about the first threat, about where the static is in a lot of these operations, so you can be aware of them. Now we're going to talk about electrostatic shocks to workers. This is much more common. Now, when I talk about ignitions, there's been fatalities due to burns. That's common. I'm sorry, not common, but it happens. An electrostatic shock to workers, there's a lot of cases of these. I had an instance where I was talking to, I teach in the Northeast Gas Association, I teach their static class at their gas operations school. And I remember talking to one of the guys on the committee about this, a static shock to electrical shock to workers. And I said, you know, I've never heard of a fatality yet from a shock. And he said, we almost had one, Dirk, up in the Northeast US. A guy got close to a piece of pipe. It arced to him, went out through his leg, and burned his toe so bad that they had to amputate his toe, and his heart stopped, so they had to resuscitate him. Pretty close to a fatality, but not a fatality. But I just want you to understand how this can occur, and we're going to take a look at these three operations where the static charge is dangerous for this. And once again, we're going to go back to squeeze off, because this is where you're going to find some of the highest voltages generated inside a pipe. It's due to squeeze off operations. That's we're going to talk about grounding tools in just a second. But remember that the tool, forgetting the tool right now, these static charges that build up inside this pipe, both in the front and in the back, if somebody gets close enough to it, it will arc from that pipe like it did that guy and go to ground through the worker. So you have to be very careful in your in dealing with squeeze off and the shocks that it can create to workers. The second thing is when you cut into hot spots into pipe. I had an incident in the Midwest or Western United States. A distributor had like an 8-inch line, and then he had a 6-inch stub line off it. Well, the air is growing, so they want to extend the 6-inch stub line. They took the 8-inch line out of service. Then the guys started to get in the excavation to cut through the stub, to cut the stub off to extend the line. They're cutting through that stub. Next thing, there's a boom, explosion. Not a fire, just a shock. 2 guys off to the emergency room. Well, the distributor, the gas distributor, was kind of embarrassed because he hadn't called for a locate. So he calls the electric company and says, sorry, we didn't call for a locate. We just cut one of your lines. The electric company says, we don't have any lines out there. What had happened is they'd cut into a hot spot and the tool grounded it and shocked the workers. And the same shock can happen again when you have high velocity gas passage, whether it's, like a purge line like that, or any kind of blowing line. You need to be sure to understand that that could be a shock hazard from the charges developed inside that pipe. Now, what we're going to do now is I'm going to talk to you now about developing and evaluating best practices, operating procedures for static ignitions and static shocks. Now, in a few minutes, we're going to talk about electrostatic pinholing and electronics burnout. There are no procedures to prevent that, and I'll explain why. So basically, what I'm going to do now is start to talk to you about how you can look at these operations we've just covered and have procedures that address preventing ignitions and preventing shocks. And the key thing in this is, now that you have an understanding of what static is, what the basics of static is in polyethylene pipe, where they are in these operations, once you focus your procedures to eliminate the charge where research has determined they exist in these operations, you're going to be able to prevent shocks and ignitions, and that's our goal. And when you do that, what you're going to do is you've identified where the risk is, you're selective in your efforts, and it's going to be cost effective because you're not just doing a shotgun approach, you're not just spraying everything or grounding everything. You're saying, I know where the static is in these operations, and I'm going to make sure my procedures take care of the ignition and shock risk in these operations. Now, when we talk about an ignition threat, we're going to start to talk about basically how to evaluate your static risk reduction SOPs. The first thing you have to do is you got to get management buy-in. Now, right now, there's 58 people on this webinar. You clearly understand the problem with this. Because you're here, that does not mean that your management has the same interest in preventing static ignitions and shocks as you do. You must get management buy-in. Alagasco, which is now Spire here in the States, their safety manager, he's since retired about 3 years ago, Tom Rayburn. Tom went through all the claims at Alagasco. And he said, Dirk, when I went through all the claims, I found that static ignitions were one of the rare ones, but they were one of the most expensive. And when you think about it, burns are terrible. They are really, really terrible. We had an incident out in West Texas, and it was a standard O&M operation. They had an ignition, and this young kid, he wound up being in, how he didn't die, I don't know. He wound up in a burn intensive care unit for 2 months, 2 nurses around the clock for 2 months. And that doesn't include the step down and rehabilitation, everything like that. Burns are terrible. So there has to be a management buy-in that prevention is cheaper than remediation. That's got to be the first thing on the list to do. Then the second thing is, now that I've taken you through some of these operations and as a starting point, you need to add, delete, reprioritize based on your operations. I had a guy call me up one time, and it was either during the launching of a pig or retrieving a pig. They had a plastic pipe as a launcher and retriever, and he said, we had an incident where we had a static ignition, the guy got burned. Do we need a static suppression procedure? Well, yeah. You got exposure to ground, gaseous mixture, worker present, you need a procedure. So you, just because I've given you these 5 dangerous operations, don't limit yourself to that. You need to look at your particular operation and say, what's necessary in some of these other operations to make sure I don't have an ignition or a shock. The third thing you got to do is you got to make sure that whatever means you're using to get rid of the static eliminates the identified static risk, that it's effective. I call this guy Bucket Man because I was talking to this guy one day and I said, so tell me, what's your static suppression procedure? You go, well, looked at his shoes and looked at me. He says, well, what I do is I pour a bucket of water in the hole and pray like hell. Okay, it's a procedure, but let's say he's doing a hot tap. The static threat is inside the tap where the tool goes in to meet the pipe. He pours a bucket of water in the hole of the excavation. He might as well throw it in the air. Didn't do a thing because it didn't eliminate the static at where the static risk is in the operation. Make sure that whatever means you're using gets rid of the static where it is in the operation. And then finally, make sure your static suppression procedures are easy to use and try to build some redundancy in it. So if somebody skips one, you know, it happens. I'm going to tell you a story a little later, just a few minutes, but it happens. And so sometimes I see some of these static suppression procedures are so cumbersome that, you know, the guys look, well, nobody's here. Okay, we don't, I've been done this long enough. It's not going to happen to me. It's not going to happen to me. I'm just going to give you two real simple to do things you can do without, as soon as you leave this webinar, you can do these two things and, you know, that'll make a difference. And the first thing is dissipate static from a safe distance whenever possible. Use remote static dissipation procedures. The purpose of static dissipation procedures is so that it doesn't ignite with a worker in proximity. A lot of times using rags, you have to put the worker in proximity to a possible ignition to apply the static suppression procedure. That makes no sense. So try to dissipate static from a safe distance. The second thing is be ruthless in your enforcement of the procedures you develop. Be consistent and comprehensive. About 4 years ago in the Mid-South, a crew of 5 from a municipality went out to do a standard O&M operation in a street excavation. Now, I know the operator, I'm not privy to the details or anything like this, but there's certain things you can take from it just from the basic facts. Witnesses said they heard a whoosh and then screams as a 2-inch gas line was blowing on fire in an excavation. There were 3 guys in the excavation, 2 guys outside the excavation. All 5 went to the hospital. Of the 3 that were in the excavation, all were critically burned. 2 survived. 1 died 30 days later from his burns. Now, my purpose is not to point fingers, not to assign responsibility or anything like that. We don't know. I can't tell you if the worker didn't follow procedure or the company didn't have a procedure. But clearly, when you have a blowing 2-inch gas line in an excavation with 3 guys and no fire suit, it is a major failure procedure. If you are not ruthless in the enforcement of your procedures, you can have a catastrophic event. Gas is very unforgiving. Static electricity and gas are very unforgiving. If you make a mistake with static electricity and blowing gas, you could have a catastrophic event. And the best way to prevent that is be ruthless in the enforcement of the procedures you develop or you already have, and be consistent and comprehensive. I know one operator that if they catch a guy not following a static suppression procedure, he's fired. That's it. No explanation. There's no recourse. No, I'm sorry. No warning. That's it, because it can be that serious. So be ruthless when you set up your procedures. Now, we've been talking about static ignition, and the static shock threat is very similar to this. And the first obvious one is you can do is you want to keep safe distances from known high voltages until at least you've externally dissipated the pipe that they could come in contact with, keeping in mind there could be a substantial interior charge. Now, a lot of times, you know, there's a grounding, there's procedures, people have grounding of tools. And it's important to understand what grounding of tools does and what it doesn't do when you think about it. Grounding of tools is only a worker protection procedure. It does not do anything to get rid of the static. You say, well, yeah, it does. If static charge goes through the tool, yeah, then the guy doesn't get hurt. Okay, well, that's true. But remember that tool, because polyethylene is not an electrical conductor, it's an electrical insulator, that tool only grounds a charge at the point it touches. So let's just imagine you got a squeeze off tool and it's squeezed off a little section of polyethylene pipe and you've got that grounded. All that does is take the charge where that metal came in contact with that plastic and conduct it to ground. And it prevents that charge instead from going through the worker to ground, okay? But it does nothing else on the rest of that pipe, nothing else at all. So it's grounding of tools, whether it's a squeeze-off tool, a cutting tool, tapping tool, whatever it is, only protects the worker and directs any static charge that tool may encounter to an electrical path to ground as opposed to an electrical path through the worker. Now, again, there's two schools of thoughts on that, grounding versus isolation. And you know what the grounding path is. We've just talked about that. The other thing, the isolation theory, and there's some people that do this, isolation electrically isolates the worker. He has rubber boots, they dry, the tool is isolated. And so what happens is the charge can't find a path anywhere to go to ground. Now, when you ground something, let's say you have a tool that's grounded. When that tool, if that happened to cut through a piece of pipe and it encounters a static charge, it's going to arc to that tool, then through the wire and then the ground. So there is going to be an initial spark, and if there's a gaseous mixture and conditions are right, that could ignite. If you have electrical insulation on the other hand, isolation on the other hand, when that tool, if that tool is electrically isolated and you made sure your policy is you can't touch ground, have to have rubber boots, you're electrically isolated, that tool goes in and cuts through a static charge, it's just going to cut through it because the charge, there's no path through the tool to ground. There are two schools on that. I'm not here to do either one. All I want you to understand is grounding of tools is not a static suppression procedure. It's a worker protection procedure, and that's important to remember. Now, we've talked about the two primary threats that I think most of you are interested in. I'm going to talk about two more very, very briefly, just so you recognize it, because static creates leaks in polyethylene pipe. And the reason I want to explain it to you is I have seen operators for years fight this. I mean, I'm not kidding, years fight this problem, thinking they've got bad pipe, and the problem is it's a static problem. So I just want you to be able to recognize it for what it is. This is a paper that was presented to the Plastic Pipe Symposium about 1985, written by Mark Staker. It was the first paper ever written about static electricity in polyethylene pipe, and it was not about an ignition. It was about the fact that when he was doing squeeze off, he noticed he started getting pinhole leaks around his squeeze off, and he wrote a paper about it. And essentially, what happens is this. If you go back to the basics that I've talked to you about, what happens is we say that static originates on the inside of the pipe. It can't go away. Mother Nature wants to go to electrical ground. So what happens, we've been talking about instances where that pipe's exposed, where you've dug it up to do an O&M operation to repair third-party damage or something like that. What happens, however, if that pipe is buried, that it is not exposed, and those charges build up inside that pipe? What happens? This is what happens. This is an electron sectional of an electrostatic pinhole in a standard yellow pipe. What happens is the static builds up on the inside of the pipe due to the friction of passing a gas. Remember, Mother Nature wants to go to electrical neutrality. So what happens is that charge then, even though polyethylene is an electrical insulator, it's not an infinite electrical insulator. Just like your polyethylene pipe will hold pressure, it won't hold an infinite amount of pressure. There's a limit. Electrically, it's the same way. There's a limit to how much voltage that pipe can stand before it fails. And what happens is that charge builds up on the inside, it arcs through the pipe to ground itself, and in the process, the heat of the arcing burns a hole in the pipe and creates a pinhole leak. And so what happens is gas research has confirmed this. The charge conditions get so high across a pipe wall that they exceed the strength of the material, and they arc through it and creates a pinhole leak. Now, in the United States, and I know up in Canada, it was, I think maybe you probably passed it sooner, but in the US, they put a no regrind rule in, that they can't put regrind in polyethylene pipe. And the reason is they think that was, in the United States, the PHMSA specifically cited in the Federal Register when they made this rule that we believe regrind is contributing to pinholes. They don't, down here in the States, PHMSA does not want pinholes in polyethylene pipe. But it's important to remember that all pipe, doesn't matter whether it has regrind or no regrind, all pipe will fail if the voltage gets high enough. If you take virgin MDPE pipe, there's an engineering constant. And what will happen is that pipe will fail if this voltage inside exceeds 510 volts, approximately, per 1,000th inch of wall thickness. Other materials will fail at different rates. But remember that the problem is static, it's not the material. So all I want you to do is to remember that pinholes are created in the normal operation of gas transport. It is not a materials failure. I have a webinar that deals strictly with this problem because this is a problem both at gas producers in the Permian Basin to delivery point. But all I want you to do is recognize that it's not due to manufacturing defects, it's static. All the lab test and failure analysis have said it is not a materials failure, and replacing a pipe is not going to solve the problem. You got to get rid of the static. Here is the last thing here on this issue of electrostatic pinholes. Down in the States, there's a newsletter circulated with fire investigators, forensic fire investigators, and it's called Fire Findings Newsletter. They sent this to me because they were getting fires at gas meters and they could not figure out what the source of the leak in the gas was. They said, could it be pinhole leaks in service lines that accumulate and ignite? Sure can. I had a gas well catch on fire in the Permian Basin because the gas line coming off the phase separator pinholed and ignited the gas and burned away the pipe. Yes, it can. So you need to deal with the problem, and it's not replacing the pipe. That will not solve the problem. Very quickly, if you have pinhole leaks, they usually occur in 1 inch or smaller plastic service lines because the smaller the pipe, the thinner the wall, therefore the less voltage need to put a hole in it. I've seen pipe with 1, 2, 3, 4, 5 holes in it. I've only seen it in polyethylene pipe, no PVC. I've seen it in medium density. I've seen it in high density polyethylene. I've seen it in every brand of pipe. And if you have pinholes in your system somewhere, they have a tendency to congregate geographically. In other words, if you're finding some service lines in a neighborhood that's got pinholes in it, you probably have them in the whole neighborhood. There's a problem in southern Indiana, northwest Kentucky, southern Illinois, Fredericksburg, Virginia, New Haven, Connecticut. I mean, it's for some reason, we don't know why, they have a tendency to congregate in geographical areas, and they're going to continue to be made unless you address the static problem. There's no standing the only way you're going to get rid of pinholes is because they're caused by interior static. You have to get rid of the static inside. Therefore, there's no standard operating best practices to reduce pinholes. You can't do it, okay? It can't be done. And if you just keep replacing the pinhole pipe, it may be cheaper to put static suppression in so you don't have to constantly be digging up stuff. Very last thing, there's only one slide on this, then we're just going to review standard mitigation technologies and a big summary, and we're done. We're going to find more and more that static and polyethylene pipe is going to burn out electronics. What happens is, remember we talked about how static builds up in that pipe. Let's say that pipe is coming up out of the ground. It has an electrical isolation joint. You got a solid state meter up there. Now, you can have 40, 50,000 volts inside that service line in voltage. If that voltage arcs across that isolation fitting, it can go through that meter and burn out those meters. All solid state electronics is designed at 2, 3, 4, 5 volts. And these service lines at pinhole, they're at voltages of 45, 50, 60,000 volts. And so what happens is, if you start to see areas where electronics is burning out, everybody assumes it's lightning. It may be lightning, but it may be lightning inside the pipe. And again, there's no standard operating procedure that's going to prevent this because it's an interior pipe problem. I was out of Kansas, and what had happened is they were doing a repair operation, and they put the transmitter. They had to locate transmitter. They connected the transmitter, locate transmitter, the tracer wire. They had traced the pipe. They dug it up. They had squeezed off the pipe. Next thing you know, 3,000 feet downstream, the locating transmitter burns up. They said, must have been the batteries. I said, no. The static electricity inside the pipe during squeeze off arced to the tracer wire, went back to the tracer wire, and that low voltage locating transmitter was toasted. The batteries inside, there was not enough energy in those batteries to toast the transmitter. So you're going to see there was an instance where the root cause, when I said in that first slide, the root cause always goes back to the static inside the pipe. That static went from inside that pipe to the tool, tracer wire, down and into that transmitter. Real quickly, we're going to finish up here. Static mitigation technologies. What I'm doing is I basically separate them based upon what surface they're going to get rid of. Static is on the exterior of the pipe and on the interior of the pipe. So we're going to look quickly at the technologies available to get rid of static on the outside of the pipe and then quickly on the inside. On the external static suppression, you have wet rags. They were recommended by the AGA back in 1970s when polyethylene's plastic pipes started to be introduced, and it was because they had nothing else. What we did is we took antistat technology that developed for semiconductors and computers, modified it for the natural particular needs of the natural gas industry, and we made our aerosol static suppressor. It's a topical antistat. And then the other thing that you have is for interior, and we have interior static suppression cartridges. Now I want to talk to you real quickly about the advantages and disadvantages of these technologies. First of all, use grounding and wet rags, and that's essentially all that happens. Wet rags simply ground whatever surface they're connected to. This is a picture of Normac's ASG system. They've since discontinued it. They recommend our product as a replacement. But the reason I wanted to show it to you because it's a cleaned up version of wet rags. You may not be familiar with it, but it was a nice cleaned up version of wet rags or soapy burlap. And essentially what happens is you see that pink film, they would wrap it around a surface and spray it with their solution, and they basically grounded it with that rod. And that grounding rod carried the charge off to the ground, and that's basically what wet rags do. You wet these rags up, they become electrical conductors, and you make sure their rag is connected to ground. Now, it's a cheap technology, it's an old technology, but there's a couple problems with it. First of all, it really doesn't solve the problem of why you're doing static suppression. You want to get rid of a static charge so it doesn't ignite in the proximity of a worker. Yet to use wet rags, you got to say, go down where there's a potential ignition and wrap those rags around that surface and ground it so we get rid of the charge. Well, you really want to get rid of the charge before the guy goes in the excavation, not make him go into the excavation to get rid of the charge. The second thing is it's a grounding mechanism. So you're assuming that when you wet those rags and have them go to ground, that indeed there's a connection. You don't know. You assume so. You hope it's wet enough, but you don't know. And then third, there's a lot of operations where wet rags just aren't suitable. You got a purge pipe in the air, or like if you're doing a hot tap, putting wet rags on the outside does nothing. The static charge is on the inside. Our external topical antistat, the IGT aerosol static suppressor, works on an entirely different theory, entirely different. We don't ground it. What happens is on a chemical molecular basis, when our liquid hits a surface, it immediately dissipates the static charge. It does it on contact without grounding immediately. So the nice thing about it is you can get rid of a charge anywhere that you can get a surface wet with our aerosol. And on the right, you see we have a reach tool that's designed so guys, when you're outside an excavation, you can be outside an excavation and dissipate the static charge and spray a dangerous situation at a safe distance. And so it overcomes it. Like with hot taps, you simply spray inside the tap. If you got a purge pipe, when you're finished purging, you just take the reach tool and you stand up there and spray inside the pipe. Or if you got third-party damage, you've done your squeeze off. You don't want anybody in that excavation. You take the reach tool and you spray from the outside and get it all nice and wet. You're done. We had our aerosol tested by the Gas Technology Institute for this reason. guys, people are creatures of habit. Your workers out there say, yeah, you know, I mean, I've used soapy rags for a long time. How do I know this really works? And we wanted to make sure it was as effective, that there's no legacy issues. If you spray on polyethylene, is it going to cause a legacy issue or everything like that? GTI tested it, and they said it doesn't affect the PE. It's effective as effective as wet burlap in eliminating static. It's non-flammable. And so that we had them test that for that reason. Now, it's important to remember when you go through and put all your procedures together, external static mitigation does nothing to get rid of the internal static charge. Here's the citation from Gas Research Institute. It's vitally important you remember that. Static is generated initially on the inside of the pipe. It creates a charge on the outside of the pipe. If you get rid of the charge on the outside of the pipe, you've done nothing to get rid of the charge on the inside of the pipe. You must respect that charge. Now, we have an internal static suppression cartridge system, and it's not a liquid. It works entirely different than our spray, but it's designed to eliminate the creation of static inside pipe, which it does. Most of our customers that are using this are doing it because they want to get rid of pinholes. They're having pinhole problems, and when they get rid of the internal static, the pinholes go away. And so it saves them a lot of repair costs. So that is designed to eliminate static inside the pipe. So that kind of gives you an outline of the technologies for external static suppression, both a grounding and a topical antistat, and then internal static suppression with our cartridge. So we also had it tested by NICOR and labs, and we were able to make static come and go in systems as we, in a neighborhood, just by bypassing it in and out. We can make static come and go at will with our static suppression system installed in the system. And then finally, we have a tool that if you want to get rid of temporary and internal static suppression, we have a tool with using a fixture from Fisher Plastics that allows you to spray our aerosol inside a line and coat the inside of the line with our aerosol static suppressor on a temporary basis. So we are done. I'm just going to go over it quickly. We're going to do a quick review. Static is normal in gas distribution systems. I have guys sometimes say, well, what are we doing wrong? We got static on our system. Static is normal. Static ignites gas, it causes shocks, it creates leaks, and it burns out electronics. Static is an injury and an integrity issue. The root cause is always the initial static inside the pipe due to the passage of gas. External static suppression will only prevent ignitions caused by external static. And it does nothing to get rid of the charge on the internal side. Pinholes are caused by internal static. That's an internal static issue. It is not a materials failure. Electronics burnout, again, is caused by internal static, and you're going to find it's probably not by lightning. And if you want to get rid of the three threats of static in PE pipe, internal static suppression is necessary. So with that, you people have been very kind to give me an hour of your time. Your time is valuable. And I've given you a lot of material. Like I said, they're going to record this. There's more than you can take in at once. But I hope it has been beneficial, worth your time in viewing. So with this, I'm going to turn it over to Mike. And if you ever want to improve your static suppression technology, then CR Wall are the people to see to do it. Mike?
Dirk, thank you. That was fantastic. Yeah, I just want to tell you, we've had a number of comments thanking you for the simple and plain language explanation. And I agree, very, very well delivered. So thank you. It's
my pleasure.
A couple of questions. One, suppression cartridges. Give me how many are needed for a small town system or a small district?
Okay.
Where do you put them? District reg stations? What's the configuration?
Internal static suppression, our cartridges can be put anywhere you want. We had one customer, in fact, I just talked to him yesterday. The city of Benton, Kentucky it's a small system. They have a 3-inch line and a 4-inch line feeding from transmission, feeding a system that has about 7,700 services. They're in Kentucky. And they have 330 miles of pipe. They were getting on the average 11 pinholes a year. They surveyed a third of their system every year, and in that third, they usually had 11 pinhole leaks on average per year. They put our 2 cartridges in at their feed station. And the following year on their leak survey, I think they had one or two leaks. And now on average, they're about 1.4 leaks. And we're tweaking the system. We're trying to find out, where there may be a little higher static, different places. But the point of it is, we essentially cut their pinholes, decreased it by 88%, and their pinhole repair cost by 88%, just by putting 2 cartridges in at their gate station. I have another Indiana distributor. He was having a problem with master meters. He was getting pinholes in a master meter system. He just put 1 cartridge at the downstream side of the last regulator going to that master meter center to solve that problem. I've had people just put it in a gate going into a city. So it really can be put in anywhere you want.
Okay. Thanks, Dirk. We have one more here, and I know we're just we're at time here. But
okay,
the question is, what principle does the aerosol static suppression works on? How does that eliminate the charge in comparison to standard static elimination techniques?
Standard static elimination technique is grounding, where you take the charge and conduct it to ground. A topical antistat works on a chemical basis to retrieve free electrons, and it bonds it to the molecule. It basically becomes part of the chemical molecule. And so that's how it basically eats the electrons and adds it to the chemical molecule. That's the difference. A real simple, quick explanation of the two.
Good, Dirk, thanks. Look, again, on behalf of Dirk and the Sierra Wall Foothills team, thank you all for attending. We can make the recording available to you, so we will please follow up with us, and we'll get that to you. Thank you all again. Have a super day, and Dirk, thanks. Take care.
My pleasure, and thank you all for attending.
Appreciate it. Bye-bye.
Bye now.